We are broadcasting at the moment. Oh, here we go. We got participants. We got 14 participants so far.
Oh, okay.
I wasn't broadcasting, so I wasn't seeing who there. I got 20 now.
Oh, okay.
Sorry about that, guys. Tom Curry here for all you participants out there in the or attendees out there in the netherworld or ether world or some weird world that we're living in this year. Not a lot on our SAC agenda today, other than to remind people that we are having elections next month. My buddy Jack and I and Kevin Kozel have agreed to remain in our positions as president, secretary, and property individual. I've yet to get a hold of David Dillmore, our vice president, to see if he will stay on as VP. But Paul has to leave as our treasurer, pursuant to the bylaws / constitution of the club. So we are in the need of a new treasurer. So anybody who wants to pony up for that, please send an email to me, Rick Rotrammel, or even Paul for that matter. And we will put you on the agenda for next week, or next month rather, sorry. Another bit of business, I contacted Grand Canyon University. Jennifer, that's where we normally have our meetings, Camelback at about 35th Avenue. Grand Canyon University allows us one of their rooms, and of course we pay them for it, but it's fairly reasonable. But due to the COVID, they have canceled everything there. And although they are restarting classes on campus, they're not allowing any outside entities on campus until at least 2021. So we are Zooming it next month in December, because I doubt we'll have a Christmas party, unless it's a virtual Christmas party. And I didn't have a whole lot else. Paul, you want to mention to people to pony up for their memberships for this coming year?
Yeah, it's time, that time of year to renew for the coming year. It's $32 for the for a single person and $36 for a family. The newsletter has my address to mail it the check to.
Okie doke. Rick, anything, or do you have your mic? Let's get your mic back on here. His mic is off. Let's see, can we get you, Rick, can you get your mic on and mention about anything on the, oh, there you go. You want to mention anything about the newsletter? Okay, his mic's back off again. Okay. I'm not sure. We are seeing all sorts of things going on. Jack, anything from the secretary end of things?
Anything from the secretary? Just agenda items that were already brought up in the email that we, I believe, are going to get discussed shortly, right?
What were they?
There was something about the insurance, and the other thing was about virtual meetings or grant. What you said about GCU is the thing that you are announcing is that we won't, you're just announcing that we won't be having any more meetings this year, and it'll be 2021, right?
Correct. It'll be 2021 before they even decide if they're going to allow it in 2021.
What you wanted to say about it, right? So no shocking news or anything from them, huh?
Yeah, I don't think that GCU surprised anybody by that move to deny us access. So,
but there's nothing new. No new business from them.
And I had hoped to get some presentations by, say, Kevin Cozell, because he keeps promising, but his grandkids keep showing up. And I can understand that. I like it when my grandkids show up, but they've moved to, well, not my grandkids, my great-grandsons have moved to Houston, so they never come by anymore. So to heck with them. I'm writing them out of the will. So today, I guess we can just jump straight to our presentation. And today's,
One more item.
pardon me?
One more item.
Oh, okay, please, go ahead.
I guess the Thunderbird Star Party for the fall Thunderbird Star Party 2020 is canceled or will not occur. You might as well put it on record.
Yeah, we can probably do that. Yeah, we had an email from someone asking if we would consider having our outreach events because, you know, we're astronomers and we're pretty much curmudgeons and we stay by ourselves anyway, distance by 50 yards apiece, and so it wouldn't be an issue. But we had to point out that if it is a club event, the liability issues are too great, and that's in conjunction with EVAC. Both groups have confirmed that no, until further notice, we will not have any official get-togethers. Although next Monday, Tuesday, I will be out at the antenna site or the emergency airfield, hoping to get.
Event, right?
Pardon me?
At an unofficial event.
That's enough. I'm just going out to the desert. It's unofficial.
Yeah. Pretty unofficial.
With some friends. It's too cold
And,
right now. So,
the other,
I'm sorry.
and with that, our insurance premium is due. I guess the treasurer handles that. But we have a $2 million liability insurance policy, and I don't know if there's anything to use it on. We don't have any liabilities, or maybe we should modify that or ask the last insurance company I know of was Liberty Mutual. I don't know who it is now, but we should be talking with them and ask them if we can modify the premium, if any.
Well, I paid the insurance just over a month ago.
You already paid it?
Well, it was for the year. It was like end of August.
Okay. Well, then for 2021, then.
We'll play it by ear.
Okay. It's been paid for this year.
Okay. I would, again, as we have mentioned in the newsletter, Rick's put in there, if you have done something, haven't just sat on your tuchus and read or played Parcheesi with your family throughout the warm weather viewing period, let us know. Maybe present something in the November Zoom meeting. Get with me or get with Rick and we'll put you on the agenda. Doesn't have to be long. It can be whatever you want. I know if you've looked at our Facebook page, Tom Palakis has done some really incredible Jupiter stuff. I don't know how he gets such clear photos. Of course, it's a 15-inch scope, but and he says from his home, it's like, you know, I won't go into the angst about all the lights around my house and the power lines behind the house, and I just can't get a clear view of anything. But that's why I'll even take off for the desert or the mountains when I can. But yeah, we'd like to see people participate. Paul's going to look at the number of our attendees who are actual SAC members, paid SAC members, to see if anybody from the club is actually watching this other than we four right now. I know David Dillmore, our vice president, can't because he doesn't have a fast enough internet to do Zoom. So and I haven't heard from Steve Dotter in a long time, so I don't know what he's up to. And Brew is normally around, but he's not here today. So I tell you what, without further ado then, let's go to our presenter from NAU, a scholar, not just a postdoctoral individual, a postdoctoral scholar. I don't know what the difference is in that. I was not much of a scholar, but so I will let you take the field. She's from the College of Astronomy and Planetary Science, and is dealing with terrestrial issues. And me being a geologist, I love terrestrial stuff. I would give anything to be able to go up with my sedimentary hammer on Mars and whack on some of the strata up there. That would just, I would just, oh, I'd be in hog heaven. So Jennifer, I am giving this to you. Take off with it. I will mute myself, and Paul and Jack, if you will mute yourself.
Okay, thank you. You should just see my slide, not my presenter view, hopefully. Yeah, my name is Jennifer Boos. I'm a postdoctoral scholar in planetary geology. Basically, just, I don't know why they call it that, actually. That's a good question. It basically just means I have my PhD. And what I study mostly is minerals, magnetism, and thermophysical properties, which could mean basically ice deposits. And mostly I study these on Mars, although I work on other planets as well. And I just want to put a plug here. Something I do in my free time is what I call House Calls from Outer Space, and they're interactive online presentations for school-aged kids. And you can find out information about those at my website, which is here. And I also do them for classrooms. And right now I have a couple, one on aliens and one on Mars, and I forgot the rest, but they've been pretty successful. Okay, so today I'm going to be talking about magnetic fields in the solar system, past and present. And this is something that I started working on as an undergraduate, and I still continue to work on it post-PhD. And I'll do a little bit of basics for everyone in the room. What is a magnetic field? Basically, it's a vector field, so it has both a direction and a magnitude, and it exerts a force on a charged particle. And so that charged particle could be something like an electron or some staticky clothes you might have. So magnetic fields are generated by the movement of charged particles. And so you might think, well, my refrigerator magnet is not moving. So how is it the movement of a charged particle? And the movement in that refrigerator magnet is actually the electrons, which are aligned in the crystal structure or the structure of that material. And so this is a schematic. It's not usually perfectly that all the atoms are aligned the same way, but the majority of them will be, and their electrons will rotate, therefore, in the same direction, and then this concerted movement generates a magnetic field. Or you could have literal movement of atoms or electrons, for example, through a wire. So anytime you have an electronic, you have charges moving through space, and you generate a magnetic field. And in terms of planetary context, what we have is what is called a dynamo. So planetary magnetic fields are called dynamos, and sometimes they're called core dynamos, depending on where the magnetic field is. But this is a cartoon that the USGS made. This is just one panel from it. But basically, if you think to the structure of our Earth, we have our solid mantle, and then we have a liquid outer core and a solid inner core. And so that liquid outer core is actually an iron nickel fluid, and it rotates in these kind of convection cells. And it because it rotates in this kind of organized fashion, it kind of self-sustains itself. But when you sum all these convecting cells of a conductive material together, and it's all the way in the core, you end up with a pretty uniform magnetic field outside of the planet. And so this is called a core dynamo. And so what are they good for? You probably know of some of the things that magnetic fields are good for. Navigation, we use them for compasses. They are super great for protecting us from solar radiation. So Earth has a magnetic field right now, and it helps sustain our atmosphere and our oceans, and protects us from things like getting really bad sunburns or cancer from the sun's radiation. And then the interaction of the sun's solar wind with our magnetic field is what causes aurora. And then geologists actually use magnetic lineations in the seafloor to figure out plate tectonics. So this is what the seafloor looks like off the coast of Washington. And what this is showing is actually, it's kind of hard to see, but the seafloor as it spreads, it records the magnetic field that's present on the surface of the Earth at that time. And you actually end up getting changes in it. And so you have this symmetric pattern. So here in this red section is where the seafloor is spreading. And then the symmetry, which we see in the magnetic field lines, shows us how the plates are moving. So there are many magnetic fields in our solar system right now. Of course, we've already talked about the Earth and the sun have magnetic fields. Currently, Mercury also has a magnetic field. We already mentioned the Earth. Jupiter has a very strong magnetic field, and 3 of its moons also have strong magnetic fields or detectable magnetic fields. So Ganymede has its own internal magnetic field, while Callisto and Europa are icy satellites, or basically they're have an ice crust and then a liquid ocean. And so Jupiter's magnetic field actually propagates through the ocean of those satellites. Saturn has a magnetic field. Uranus and Neptune all have a magnetic field. We don't know about Pluto because we have not sent an instrument that could detect one to Pluto. But Pluto being so small, we would not expect it to, nor would we expect any of the other dwarf planets to have a magnetic field. In the past, however, our moon also had a magnetic field. Actually, this is Mars is supposed to be showing up here. Sorry, I think I accidentally covered it up. Mars also had a magnetic field, and I'll talk a little bit more about how we know that. And Venus is actually a mystery. We don't know if it had a magnetic field. We know that it doesn't today, but it could have had one in the past. So the magnetic fields in our solar system are generated by a variety of things. Again, the magnetic field just needs to have basically a conducting fluid moving. And so on the sun, the magnetic field is generated by plasma. In the terrestrial planets, so Mercury, Venus, Earth, the moon, Mars, and Ganymede I put here too because we suspect that the magnetic field, these all come from iron in the core. Saturn and Jupiter have actually liquid helium that's rotating, and that's what's generating their magnetic fields. Whereas Callisto, Europa, Ganymede also has an ocean, as well as Uranus and Neptune have what we think are brines, or like salty solutions, oceans basically, that are generating the magnetic fields. And I see a question.
Yes.
Why
Jennifer.
does
Oh, yeah, go ahead.
Why does the Earth's magnetic field reverse? Are other small magnets that do the same? I will get a little bit into this. It's it reverses because it becomes unstable with time. And yes, many magnets actually kind of go through the same thing. I'll touch a little bit more about that later, or you can feel free to ask me again if you still have questions.
I also have a question for you about the magnitude of the magnetic fields, especially Jupiter's. I've heard that it is so massive that it's going to be dangerous to even get near Jupiter because the magnetic field itself is radiation. Is that true?
Yeah. Yeah, so there's a lot of interaction from Jupiter's magnetic field. So it interferes with, it would interfere with electronics for sure. So actually this next slide, I have comparison of the strength of the bodies. Oops. Oh yeah, there we go. The strength of the magnetic field on the different bodies. And so I put Earth as 1 just for comparison, but yeah, Jupiter's magnetic field is like 20,000 times stronger than Earth's magnetic field. It's not this, I don't know why that keeps changing. It's not the same kind of radiation that is coming off the sun. So I don't think it would be like as harmful, but it would definitely be something that needs to be considered in terms of like electronics and other types of things that we might send to Jupiter. But that's a good question. I'm not sure about like the danger of it. So yeah, the sun's magnetic field obviously is going to be the strongest one in our solar system, 3 × 10⁻17 times stronger than Earth's magnetic field. Mercury's magnetic field is pretty small, 0.006 times Earth's magnetic field. Ganymede's is actually bigger than Mercury's, it's 0.01 of Earth's. And then they kind of get smaller as you go further out into the solar system. And so you heard me mention just a little bit ago about how some of the magnetic fields are generated in the core, but some are generated in oceans instead. And so here what I'm showing is how the magnetic field, if it's a dipole or basically has a north and south, aligns with the rotation of the planet. So Mercury's magnetic field is almost perfectly aligned with the rotation of the planet, whereas ours is about 23 degrees offset. So our current magnetic north is actually somewhere in Canada at the moment. Jupiter's is slightly offset. Ganymede, and this is probably a result of Jupiter's strong magnetic field, but Ganymede's magnetic field is actually antipodal to Jupiter's. So basically the north of Ganymede's magnetic field is the south of Jupiter's. Saturn is, they're about the same. And so here's where it gets interesting. Uranus and Neptune, their magnetic rotation or their magnetic dipole moments do not cross the ecliptic, or they're not in the same, they don't basically go through the center of the planet. They're actually generated about 1/3 to 2/3 of the way to the surface. And so that's part of how we came up with this idea that these magnetic fields are generated by oceans or brines or more superficial materials rather than the core of the planet.
Another question for you.
Yeah.
In respect to Ganymede and Jupiter, then, do they act like, because Ganymede does have a magnetic field, whereas our moon used to, but doesn't now? Does it work like two magnets, the attractive positive to negative versus north and south? You'll not have a north to north, or or am I thinking wrongly there?
So I think that in terms of Ganymede has both its internally generated magnetic field from its core, and then it has an induced magnetic field from its like oceans. And I believe that those two fields are antipodal also. So the ocean field, which is induced, is basically in alignment with Jupiter's magnetic field because those are able to rotate. And then yeah, I suppose it would cancel out with the internal field. But I have to follow up with you on that on terms of forces related to Jupiter. I believe it's a stable orientation that it's in, and that's part of why it is a direct antipode. Oops. So how did we get magnetic fields? So at the beginning of the Earth, or the beginning of the solar system, we had all these molten bodies. And so here I'm representing molten as this like lighter red material. that's supposed to be liquid. And then once the planet starts cooling, you start getting a crust, and you also start generating a core. But you still have a significant amount of liquid material. And so at this point, for example, on Earth, well, so this happened first on the Moon and Mars because they're smaller, but you have what's called differentiation. And so you start to have separation of elements based on their weight. And so iron, being pretty heavy, is gonna concentrate. And so once you have this more stable cooling of the planet, less like just turbulent boiling rock and more like a steady state of heat loss, then is when you start generating these conducting cells of liquid iron. And so, like I said, for Mars and Moon, which are much smaller planets than Earth, this happened a lot more quickly. So just a couple 100 million years after the start of the solar system. Whereas for Earth, we think it probably happened like 1 billion years after the planets formed. And how do magnetic fields stop? One idea is that the planet eventually just cools all the way, that there's not enough heat escaping to sustain the magnetic field. And another idea is that an impact might disrupt the rotation of the liquid inside the core, and that would cause the magnetic field to stop. And we have some evidence. This is not by any means like a completely accepted hypothesis, but on the Moon, one interesting thing that's been observed is that there are magnetic anomalies, or very strong magnetic remnant magnetism on antipodes to where we have large impact basins. And so because impacts can generate plasma fields, the idea is that if the Moon had cooled, but the rocks on it were magnetized, which I'll talk a little bit more about later, the plasma from that impact could actually push that magnetism to the opposite side of the Moon and cause a magnetic anomaly there. But these are transient fields, so they would only be like within probably less than an hour after the impact. So comparison to planetary magnetic fields, the sun has a very distinct solar cycle. So it's 11 years, which are correlated with the ebb and flow of sunspots, which you might have observed. And this also corresponds to the reversal of the sun's magnetic field, similar to Earth's magnetic field reversals. And so the other thing that you may have heard about are solar flares. And this is basically when the magnetic field lines on the sun kind of get wound up, and then eventually, well, the way I've heard it described is they snap, and they it's no longer sustainable, so it'll shoot off some charged material, and that's where we get these solar flares. On Earth, we also have reversals, but it's highly variable. So down here on the bottom, this is just a geologic timescale where black is our current magnetic field direction, and white is the opposite. So where our North Pole would be on the south. And you can see that with time, our magnetic field has flipped many, many times, but it doesn't seem to be very periodic. And in fact, there are some periods of time where the magnetic field didn't switch for a very long amount of time. And these are called supercrons, and they are a mystery. I don't think we know very well either why our magnetic field is flipping. We could guess that the convecting cells are no longer sustainable in their current orientation, and they might move to something else more favorable, or other hypotheses. But some people have suggested that subducting tectonic slabs could periodically disrupt the cooling of the core. So basically the slabs, these tectonic slabs, as they dive into the mantle, they're a lot colder than the mantle. And then when they hit the core, they kind of shock that really hot outer core, which could cause the magnetic field to be disrupted for a little while. or impacts, although we haven't not had any large enough impacts for a very long time. Some studies try to tie these magnetic field reversals to mass extinctions, although this is also not a widely accepted hypothesis. So you might have heard me talk about remnant magnetism already, and basically how rocks can record magnetism. And this is essentially the core of my magnetic field studies. Basically, we can look at rocks from Earth or other planets and learn a lot about the magnetic field from those planets, from those rocks. So we can learn about the magnetic field generated from the core of a planet from a rock on its surface. And so this is what we call remnant magnetism. And so basically, remnant is the rock is recording the magnetic field from when it formed. So that magnetic field remains in the rock. And there are many different types of remnant magnetism, and I'm going to go through a few, but they sum up. So when you pick up a rock outside, it's going to be most likely weakly magnetized. Like you would not be able to put it on your fridge, but it actually, if you took it into the lab in a controlled environment, you could measure its magnetic field. And so that magnetic field is going to be a result of both when the rock either cooled or was weathered or was touched by another magnet.
Jennifer,
yeah, go for it.
In orientation of the magnetic crystals or whatever the sensor is in the rock, I know that they can pick up a rock and they can determine the magnetic orientation, but I don't understand how that can work unless it is actually in a sedimentary strata where they know the alignment of the strata versus a rock that's rolled down the hill. Can you explain that a little?
Yeah, so most magnetic studies on rocks are using rocks that are still bedrock or like in place rocks like you suggested. It doesn't have to be sedimentary, it could be igneous or a metamorphic rock, but an in-place rock, whereas float rocks, which are rocks that have basically fallen, those you can figure out things like how strong the magnetic field was, but you couldn't really figure out what direction it was pointing for the reason that you mentioned. It's like you wouldn't know how it was sitting when it formed. And so float rocks, actually most of the rocks that we have from the moon. So even though you can't tell the direction of the magnetic field, you can still use them for very important things like figuring out the history of the magnetic field in terms of like, if you know the age of the rock and you know how strong the field was, you can kind of figure out when did the magnetic field start and when did it stop. So I'll talk a little bit about how these rocks record magnetic fields. And so this is just a cartoon of a rock. And what I've tried to illustrate here is that there are a lot of different minerals in the rock that might be magnetic. Most rocks have something that's like maybe slightly magnetic. And so in any given rock, there's probably like a billion. Here I'm just showing a handful. But let's say this is an igneous rock or a lava rock, a basalt. So it's really hot. So it's above what we call this Curie temperature, which I won't talk too much about, but basically what this means is that this rock is so hot that it has so much energy that it's these magnetic particles are gonna align weakly with the magnetic field that's present. So this these blue lines, these blue arrows represent Earth's magnetic field. And so this rock, while it's really hot, is gonna align preferentially with Earth's magnetic field, but it's not super strong. Now, if you were to cool the rock, these magnetic particles become locked in place. And so they're not spinning as wildly around. And so the rock becomes slightly more magnetic. What you'll notice is that these arrows are not perfectly aligned with Earth's magnetic field. So magnetic particles, say they might be like a needle-like shape or a bar, they're gonna align along their long axis. That's just the most energetically favorable, but they're going to align along the axis that's most in common with that field. So take this particle, for example. This direction is going to be more similar to the ambient magnetic field than if it were pointing the opposite direction. And when you have a billion magnetic particles, when you sum them all up, they're going to record that ambient magnetic field pretty well because they're all vectors. And so if the magnetic field were to decline, as what happened on the moon and Mars, that rock would still remain magnetized for geologic timescales. So there's another way you can get magnetism in a rock is through chemical remnant magnetization. And so here's just a rock. I'm saying this is an iron carbonate for the sake of simplicity, but something that's not super uncommon. And say you heat that rock is going to undergo some chemical changes, and it may start to precipitate an iron oxide, in this case magnetite, as well as some gases. So as that heating continues, those magnetic particles grow, and as they're as they're continue to grow in this magnetic field, eventually they reach a size that is large enough to start recording the magnetic field. And so this rock becomes magnetic after not too long. And if that field were to be removed, that rock would record that magnetization. So this, Tom, this might be a little bit more similar to what you were talking about, sedimentary rocks. But basically, in a water column, sometimes you could have magnetic particles falling through the water column, and they are deposited in line with the magnetic field. Although you might notice that gravity here plays a role, as well as perturbations in the water column, so it's often not a perfect match. But sometimes we actually have magnetic bacteria that die, and they are a significant portion of the magnetization in these sedimentary rocks. And then on a planetary surface or a really old ancient surface that might have experienced a impact, you might have a rock that's magnetized and then a different magnetic field. So say this was the moon, and the moon's magnetic field has changed direction. This rock is no longer in alignment with that new field. And then you have a impact come. And if you remember, I talked about these plasma or shock waves that are generated from this impact, and they cause crystal changes within the rocks, which in the end result in the rock being remagnetized in the same direction as that external field.
But the direction would be towards the impact and not away from the impact, because I would think, yeah, that's weird to me.
Well, so this was just illustrative. The ambient magnetic field in this cartoon example is pointing toward the impact, but it could be pointing this is basically just the shock field causing the crystal changes in the rock to realign with the new magnetic field. So the direction of the ambient field here and the fact that it's pointing toward the crater, it was just coincidence. But I don't think that, well, so a plasma generated field or a shock field, I don't know what the structure of that field would look like. I think it might be very chaotic though. But this is just showing that when you have crystal changes from shock, that you can remagnetize a rock.
So it would not be like taking a nail and smacking the flat end of it with a hammer, which magnetizes the nail preferentially along that strike orientation.
No, this is more like you have 1 billion tiny particles and you like perturb them, or you cause them to have a shift, and so they're gonna, when they re-equilibrate, they're gonna like snap into the orientation that's most favorable. which will be the orientation of whatever magnetic fields around them. And so similarly, if you like touch a rock with a really strong bar magnet, you can remagnetize it because the energy from this magnetic field will be strong enough to overcome that energy that's needed for a magnetic particle to flip its polarity. And so we can kind of unravel a history of a rock and the history of the magnetic field from the planet that it came from in the lab. And as I've mentioned a couple times now, magnetic field magnetization is a vector. And so in this just cartoon, this rock has 3 different types of magnetization. It has a thermal component, or when the rock cooled, a chemical component when it got reheated, and then it got touched by a strong magnet. And when you pick up the rock, you measure this black vector, which is the sum of these 3 vectors. And in the lab, you can actually preferentially remove magnet. You basically cancel out the magnetization of particles based on their size, for example, or it's called the coercivity, basically how easy it is for a magnetic particle to switch its polarity. And so you can uncover the different vectors that make up your final magnetization. And so there are many magnetic mysteries. Mercury, we wonder, how does its magnetic field survive being such a small planet? Why does it still have a magnetic field? Why didn't its magnetic field die like Earth's moon or Mars's? Venus, we don't know if it ever had a magnetic field. And now that I've talked a little bit about the effects that temperature has on recording magnetic field, some people say that it's too hot to have recorded a magnetic field, or basically the magnetic particles never were able to snap into alignment with the magnetic field. There's too much energy. Earth, we had this question, why does the Earth's magnetic field reverse? So it's a huge mystery. There are some of the hypotheses that I mentioned previously, but I don't think that there's a consensus on that answer. On the moon, how and why, I mean, when and how did the dynamo persist? So we know that the moon had a magnetic field, but we don't know when it started or when it ended, or how strong it was. We have some ideas. And then Mars has a couple of magnetic mysteries, one of which is that it's super strongly magnetized. There are magnetic anomalies on Mars that are about 1,000 times stronger than magnetic anomalies we have on Earth. And it being such a smaller planet than Earth, that's kind of a mystery. Does the magnetic field decline on Mars have to do with the end of the atmosphere? We know now that Mars had significant water on its surface, and now it's a pretty dry planet. And it's quite possible that the decline of Mars's magnetic field coincided with the loss of its atmosphere and its water bodies. And then the last thing is that we have meteorite from Mars, a very famous meteorite that some scientists argue has magnetofossils, or basically bacterially generated magnetite. And this was a very famous rock in the 90s, but it still actually remains a mystery. And so I have studied these 4 topics, and so I am prepared to talk about any of the 4. So I wanted to ask, I guess, the panel, or if anyone wants to voice their opinion, I can delve into any of these if there are any strong preferences.
The magnetism versus gravitation, say Jupiter, the pull of Jupiter for launching something around versus any magnetic field. I mean, I would imagine the magnetic field is inconsequential versus the gravitational field. Is that true?
Yeah. The escape velocity on Jupiter is probably going to be the much harder to overcome than any magnetic field interaction.
What I read some time ago about the magnetic field of Jupiter being so detrimental, and I can't remember exactly what it was, and it was probably electronics, that it would fry electronics within, I mean, you couldn't get within thousands of miles of the planet. I'm not sure how that works. Anyway, so yeah, pick any topic that you want. They're all interesting. I think they're all fascinating.
Okay. Yeah, I think now that I thought about it a little bit more, I think probably a part of why it's dangerous is because, in relation to Jupiter, is because Jupiter has such a strong magnetic field that it's going to have a really strong interaction with the sun's magnetic field. And in the same way that Earth's magnetic field deflects the sun's magnetic field, there's probably a band of radiation that's concentrated because of that repulsion. That might be the really dangerous part of interacting with Jupiter's magnetosphere. Okay, so I'll start talking about the moon. I'll do two. I can talk about the moon and then magnetofossils, because those are pretty fun. So the moon, how and why did the dynamo persist? I mean, when and how? So here's a picture of an Apollo astronaut collecting some rocks on the moon. And so we have many, many rocks from the moon from the Apollo missions. So the astronauts took geology classes basically up here in Flagstaff and around the US to learn how to identify rocks that would be good for a study on Earth. And some of the rocks that they picked up were for these magnetic studies. And so in the lab, we're able to determine the age of a rock through radiogenic dating. And we're also able to determine the strength of a recorded magnetic field. And so this is showing the history of what we know about the moon's magnetic field. So we know that these old rocks that are about 3.5 to over 4 billion years old, record a pretty strong field. So for reference, the Earth's current magnetic field at the surface is about 50 microtesla. So these are within the range of that strength. And then we know that young rocks seem to also record a magnetic field, although what we have are upper limits on their magnetic field. So we know that the magnetic field cannot be stronger than these values. And so we don't know too much about when it started or when it ended. And these are two topics that I was able to study. So this rock here is Troctolite 76535, and it's been described as the rock that keeps on giving and the most interesting sample returned from the moon. I think these are quotes from astronauts. And so it's the oldest known rock that we have from the moon. It's 4.2 billion years old. And you can see it has some pretty large crystals. And so we were able to study this rock, taking out crystals from it and then measuring their magnetic properties. This was me when I was an undergraduate at Johnson Space Center with my two advisors. We went to the Lunar Receiving Lab and collected these samples there after applying to work with them. And then this rock here is the youngest rock that we have, that we know of from the moon. So it's actually kind of two rocks in one. It's like a grayish basalt, and then it has this glass on it. And so the glass, the best estimate for the glass that we have, the age, is 9,000 years. So that's shockingly young for any rock, especially a rock from the moon. That's like, you know, early humans could have seen the impact that generated this glass. And I actually have, if you go onto NASA's website, you can listen to the Apollo recordings. And I was able to find where they found this rock, the astronauts. Is that sound coming through? Can someone confirm that?
I'm not hearing anything yet. I don't know if your volume on that particular contact on your right side of that was up. You know, it's
Uh,
yeah, but that
yeah, I think, 1 second. I think I need to audio. Uh, same as system. Did you hear it that time?
negative.
Oh, okay. I'll try one more and then I'll just move on.
And it might be on something I need to turn on too, and I can't figure out what that would be.
I thought I just had it. Select a speaker. Okay, this will be the last time. I don't know if you guys heard that, but anyway, they find a rock and they say, here's a rock they'll be glad to see in Houston. Look at that, it's got that black splatter on it, or that glass splatter. And then they talk about it for a minute or two about how happy they're going to be in Houston to get this cool rock. Okay, so yeah, basically these two samples are giving us, are shedding light on both the start and the end of the magnetic field on the moon. And the way we're able to study these samples actually is that when they collected these samples, they documented everything religiously. And so they took the samples and they cut them and then divided them up among the scientists. And as they cut the samples, they made these like pretty awesome cartoon drawings of the samples. And so these four pieces here were actually the samples they gave us. And because they gave us these four tiny pieces, and we know how these pieces were oriented relative to each other in the rock, we can use them as basically four samples of the same spot on the moon. So Tom, you had asked about float rocks, and so this is basically a float rock. But if you can say that you have four rocks that are from the exact same time and position on the moon, you can use them as independent samples. And so what we would do is we first measured the orientation of the magnetization of these four rocks and saw that this is a polar diagram, so these are vectors from the center. We saw that they're roughly aligned. But then when we started unraveling the magnetic history of these samples, what we saw is that actually, although the samples are aligned at present, their past magnetization indicates that they were not aligned. So basically, each of these samples has a magnetic direction that's different from the rest. And what that means is that this rock, this 9,000-year-old glass, formed after the decline of the lunar magnetic field. Because if the moon's magnetic field was still active at 9,000 years, then these four samples would have all preserved that same orientation.
These samples, or this one large piece that they cut it from, it was very homogeneous. So it was like a piece of nice obsidian, or was there enough variability in it that of the mineralogy that it would cause that change in magnetism?
So the glass was pretty much homogeneous. Actually, so the glass was homogeneous amongst itself. So this black here is the glass, and then this grayish stuff is the basalt, and the basalt was homogeneous for itself, like amongst itself. But the glass and the basalt, we treated them basically as two distinct samples because they had such different ages. The basalt itself was like 3.2 billion years old. So does that answer your question?
Yes, that'll do it.
So this is how we measure the samples. This room is a magnetically shielded room. And so it uses mu metal, which is a material that has a ability to basically capture flux lines. And so it kind of sucks in the magnetic field of the Earth into its structure, so that when you enter within it, there's very little magnetic field. And so the magnetic field outside is about 50 microtesla, and then the magnetic field inside is about 23 nanotesla. So orders of magnitude different. And we put our samples into this chamber, which has additional magnetic separation, and then we're able to measure these extremely tiny magnetic fields. So one of the explanations that we thought might explain why the glass seemed to be magnetized is that we thought maybe this rock was magnetized, and then that magnetic field died. But the rock itself is like a weak magnet, and when that glass splattered on it, it interacted with the rock's field. So we basically measured the glass separate from the basalt and tried to see if we could figure out what that field would be. And so this involved basically generating a 3D model of the basalt, and then we knew what the orientation of the magnet was. And so we were able to predict what it would be at the locations of the glass. So here we have our magnetized glass, our magnetized basalt, and then we measure at the locations of the glass what that direction would be. And in the end, it was not a good explanation. So in green was our predictions for how the glass should be magnetized if it were actually recording the magnetic field of the rock. And in red is what we actually measured. So they were not in agreement, unfortunately, for our idea. But it was not a total loss. This work ended up in 2 different publications. And what we determined was actually this glass is one of the best recorders that we have of magnetic field, because it's so fine grained. It's able to record the minutest of fields. And it was actually an artifact that we were picking up from our processes. And so because moon rocks, they give us like milligrams of it, it was particularly susceptible. But it was an interesting study to see that the moon had these excellent recorders. And so this first paper is basically saying that some samples that don't record a magnetic field doesn't mean there was not a magnetic field there. And then my paper basically says that the glass was magnetized, but not from the ancient moon. And then as for our really old rock, we found that it recorded a very significant magnetic field of around 1 microtesla, which is much weaker than today's magnetic field, but a significant field. And it was like pretty remarkable data that all kind of lined up. Here you see that all of the subsamples of that rock are pointing in the same direction, showing that magnetic field was significant. And so this was from 4.2 billion years ago. So at the time, this was the earliest record we have of a magnetic field. I think now we have one that's slightly older. And so this allowed us to put a little bit more data on this plot, basically saying that we know that the lunar dynamo existed at least 4.2 billion years ago, but that it has not existed in very recent history. So I'll talk about what.
Before you go on to magnetofossils, the collision supposedly that created the moon onto the Earth Would that be the source of that dynamo on the moon? And what would that collision on Earth, or was Earth too hot then for that collision to change the magnetic characteristics of Earth?
Yeah, so that it would be the latter. So the Earth moon impact, the impact that formed Earth's moon happened really early on in the solar system's history, and so there was likely no dynamo, or if there was a dynamo present at that time, we have no record of it. It would have been during like a molten Earth time, before we had like stable sustained cooling from the core. But you might have seen here, these are kind of all a summary of all the ideas for how we might have generated a core. And so pretty much now we say there's no dynamo, but like when we thought there might be a dynamo in these really young samples, the idea was that maybe the core is still undergoing some like minute crystallization. And so it was generating a field, but it's not necessary because these samples are likely just not magnetized. But there are other ways that you could have generated the magnetic field on the moon, including impacts and different types of convection or precession. Are there any other questions on the moon's magnetism before I move on to Mars?
No, but there is a question later on about cometary tails and the potential for magnetic fields from them, if you'll get to that later.
Okay, yeah, I'll answer that one after the magnetofossils. I wish I could get my sound to work because this also has an audio clip. But basically, we have a sample from Mars, and the way it got to Earth was through an impact. So this is just an artist drawing, Don Davis, I think is the artist, of Mars, and then something impacted Mars, shot a rock off. That rock floated through space and eventually landed in Antarctica, where we found it as part of a meteorite hunting expedition. And so this sample is called ALH 84001, and that ALH stands for the Allen Hills, which is in Antarctica where it was found. And then it was found in 1984, and it was actually the first sample that was found that year. And as soon as they found it, they looked at it and saw that it's quite an interesting rock. It's got the glass on it, but it also has this kind of Earth-like material on the inside. And so they were pretty sure it was going to be interesting. And so in the field notes, when they picked that rock up, they wrote, "Yowza, yowza." And this rock has been studied, maybe like one of the most studied rocks in the world. But it actually preserves evidence for the ancient Mars dynamo. So this was, I think, the first direct evidence we had for that Mars had a magnetic field. And so this study by Weiss et al. In 2000 showed that in the interior of the rock, if you remove a sample and you measure it in the lab, it is magnetized. And one question I get all the time is, how do you know that's not from Earth's magnetic field? And so I'll answer that right now, which is that you might see this black stuff on the top of the rock. And this is glass that was generated as it entered Earth's atmosphere. And so if you measure the magnetization of the sample from the edge of the rock to the center, you actually see that about the first inch into the sample, that rock is unmagnetized. And so that's because it got really hot and it basically erased the magnetization that it preserved. But as you go further into the sample, you start to see a pretty stable magnetization, showing that the interior of the sample was not super heated. And this therefore is recording the magnetic field prior to having landed on Earth. And considering there's no significant field in the interstitial space, the hypothesis is that it was magnetized on Mars. And so in 1996, this paper came out search for past life on Mars, possible relic biogenic activity in Martian meteorite ALH 84001. And basically this sample had a couple of really interesting things that was argued to have been a result of life. And here is a quote from the paper. Although there's alternative explanations for each of these phenomena taken individually, when they're considered collectively, particularly in view of their spatial association, we conclude they're evidence for primitive life on Mars. So there were these things that they thought looked like worms, and there are these pancake-like features that are carbonate. So this rock basically formed and then was fractured, and fluid filled the fractures and formed these carbonates like we would have in a liquid water on Earth. And the rim of the carbonate has magnetic particles, and these magnetic particles look almost exactly, or some say exactly, like particles that we get in magnetotactic bacteria. So on the left here are magnetic particles from the meteorite, and on the right are magnetic particles from bacteria. And these bacteria particles are so distinct. They are chemically pure. They have a very distinct shape. It's called a hexaoctahedron. They're a very specific size, which is preferential for tracking the magnetic field. And so this is actually the main thing that's still argued about in terms of this meteorite. Most people don't believe these are worms or anything, but how do you get such strikingly similar magnetic particles in the meteorite is an active debate, because it has never been there's been no explanation for how you could do this in a non-biogenic method. Basically, nature doesn't create such, like, I mean, not, well, life is nature, but chemical processes wouldn't create such pure, specific crystals. And so this is just showing that this is still a debated topic. And so the two hypotheses for how these magnetic particles form is either through chemical remnant magnetization, or basically the rock was shocked and formed these magnetic particles, or through biogenic origin. So people are arguing that these were magnetic bacteria. And since my audio is not working here, I'll just tell you, there was a press conference with Bill Clinton where he was like, this rock might hold the mystery of the universe, basically. We should listen to what the rock has to say. So it's a pretty cool clip. You can find it on YouTube. But basically, we did a couple tests saying that if the rock was formed chemically, it would be pretty efficiently magnetized, because the magnetic particles form in the same direction as the ambient field. Whereas if it were magnetized through a sedimentary process, it would not record the field as well, because it's subjected to gravity and Brownian motion and such. And so this test is called the Fuller test of NRM, but basically the more toward this corner you are, the more efficient it is. And so we were trying to see, where does this rock fall? And then the other test we did is, like, if you were to generate a magnetization chemically, your magnetic particles should be pretty far apart or evenly spaced. Whereas if it was formed in a water column, they should clump together. So we basically measured how clumped they were. And we did it using this instrument called a squid microscope on these incredibly small fragments, 150 micron. And what we found is that it's a super efficient process. So this favors a shock origin or non-biogenic origin, but it's also, they're also clumped. So that would favor the biogenic origin. So our two tests were kind of inconclusive. So we did this third test that kind of looked at how does the magnetization behave? Does it look, when you demagnetize it, does it look like something thermal or not? And what we found actually is it looks like a shock origin. So it was not we don't have any definitive evidence for it being biogenic. So the fact that it's clumped indicates that it could be biogenic, but there's no direct evidence for it. And the fact that it's a highly efficient process kind of points towards shock. So yeah, I think I've talked for about an hour now, so I don't want to go on, but I'll answer these questions now. And if there are other questions, I'll look in the chat. Okay. Cometary tails seem to be affected by the sun's magnetic field, causing off-axis striations in the tide dust and gases. Do comet tails themselves have electronic charges and or moderately significant magnetic fields? I can answer part of the question. So I don't believe they have moderately significant magnetic fields. I think they're too small to generate their own magnetic fields, but they likely are conductive, so that that's why they're affected by the sun's magnetic field. The particles that are off-gassing the comet are charged. Other questions? I only see these two.
Yeah, I didn't see any other questions. If anybody has any, please crank them out on the Q&A pretty quick here. You know, I don't want to tell you how old I am. You saw my face, so you know how old I am, kind of. I mean, Fred Flintstone was one of our grad assistants, but it's just blows my mind what they've discovered and what they've been able to come up through geologically. I mean, geology always got a bad rap for not being much of a science, but this is some real interesting geologic stuff.
Oh, I agree with you 100%. I mean, yeah, geology does have this like connotation of being a soft science, like too open to interpretation. But I mean, we have like the fields the things that we do in to kind of unravel these magnetic mysteries involve, like, you know, understanding the physics of these magnetic particles and interactions with planetary fields and how to date things using radioisotopes and all that stuff. And the reason that I got involved in this line of research is because I really wanted to work with moon rocks. And so this lab allowed me the opportunity to go to Houston and see the Lunar Receiving Lab and look at these rocks that the astronauts brought back.
Yes, that would be cool. Yeah, I did. I worked with one of our professors with hematite framboids in coal, trying to analyze some coefficient of sulfate generation for the combustion. But yeah, that was simple science versus looking at such a small. What was that camera again that you were talking about? It looked like it had a multi-shielding, and yeah, we had a X-ray diffraction microscope, but nothing that cool.
Yeah, so that was basically extremely well magnetically shielded. That is it's called a SQUID microscope. It stands for Superconducting Quantum Interference Device, and it's basically how we measure these extremely small magnetic fields. There's one more question here. Could you comment about the magnetic fields of Ceres, Vesta, and other large asteroids? So I don't believe that those have any magnetic fields currently because they're too small. In the past, they might have had small magnetic fields or very transient ones. The one planetary body that's small that I couldn't comment on is Psyche, where they're sending a new mission. It's a metal asteroid. That's actually the person in charge of that's at ASU. And so the idea behind that asteroid, well, they don't really know it. They know it's like a metal asteroid, and they think it might be the core of a planet that has been stripped of its rock. And so it might be extremely strongly magnetized. But basically you need a relatively large body to to get a significant magnetic field. And then, is the upcoming return to the moon likely to bring back more rocks for this type of study? Yeah. The great thing about this study is these kinds of studies is that almost any rock is useful for it as long as you don't touch a huge magnet to it. So I'm sure there will be more studies on moon rocks. And one thing you might have noticed is that we have this gap in data, and it's because we don't have any moon rocks of this age actually. And so hopefully future missions can kind of fill this in a little bit. Do you have anything to explain about the Dutch moon rock that turned out to be fake? No, I don't know about that, sorry.
A question for you about the magnitude of impact it would take. It's like when they're bringing the rocks back, how packaged do they have to be? If they would drop it, say, on the hard concrete floor, could that affect the magnetism within? Now, granted, if it's due to crystallization when the rock is hot, I could understand the preferential alignment and stuff due to temperature, but just magnetism itself, again, the analogy of hitting a nail with a hammer, preferentially aligning some of the iron in it to cause it to be magnetized. How sensitive are rocks to changes in their magnetism?
Yeah, they're not sensitive in terms of like physical impact. So you need a really strong force to cause the crystal changes in a rock. So large impacts can generate these really strong pressure fields that can cause these minute crystallographic changes. But it's not so hard to alter a rock's magnetization through strong magnets, like those rare earth magnets that are pretty common these days. If you were to touch one of those to a rock, you would pretty much render that rock useless for magnetic studies.
Interesting.
Yeah, it has to do with actually when the rocks cool and they record the magnetic field, the crystals have already formed. It's that the electrons within those magnetic crystals are still like spinning wildly at the high heat. And then once it cools, they become more stable. But yeah, you basically need really, you need to cause a crystal change in order to remagnetize a rock. Is there any correlation between the Earth's magnetic reversal and global events? Mass extinctions, rise of life forms, ice ages, global warming. Yeah, so there is some correlation between mass extinctions and magnetic reversals. It is, there are a couple papers about it. It's not any of the major mass extinctions like the, for example, the dinosaurs dying or anything like that, but there are some smaller extinction events that seem to be around the same time as magnetic reversals. But we have so many magnetic reversals and not so many large extinction events that it's a little bit harder to say that they're actually related. We do know that many organisms use the magnetic field for navigation.
Okay, last call on questions. See if anything's coming up here. Not in the chat. Not that I can see.
All right, well, thank you for hosting me, and then oops, sorry, this is from an old presentation. You're obviously not the Prescott Astronomy Club. I'm sorry. But here's my email if anybody would like to have a follow-up question. And then again, my my website here if there's any interest in a house call from outer space. I guess this one's more appropriate. But yeah.
Well, thank you very much, Jennifer. Do appreciate it. I'll get with you offline for some stuff here. For the rest of you all, thank you for attending. Again, please, if you want to present some of the some of your what I did during COVID, I would appreciate it. And I think some of the other club members and visitors to the Zoom meetings would enjoy seeing it. So let us know. Otherwise, nothing else. Anybody else have any questions or comments? We can mic back up. Let's see if I can do this. Okay, okay, I'm gonna play with your video here.
Oh, I can stop sharing.
Okay. Okie doke. Any of our board members, SAC board members, have anything they want to bring up? I think Jack, it's you and me, and Paul, I guess, has timed himself out or something. So that being the case, until next month, I will send out the emails, and I promise I'll start broadcasting earlier so that I won't think that there's no attendees at the meeting. That's my problem. That's, again, operator error. I'm new at this. I'm old. I don't understand these young people's things. What'd you say, Jack?
Always technical difficulties.
That's it. It wouldn't be fun if you didn't have them. Okay. That being said, guess what? I didn't gavel us in. I'll gavel us out, though. And the mysterious disappearing gavel. That is so cool. Okay, until November. Thanks again, Jennifer. Thanks for you.
All right.
We'll talk to you later. And we'll see, stop by our